Welcome back for the chapter 4.5 video. After learning some of the properties of logarithms and how they can exchange to different things with exponentials, we're now going to tie that all together and learn how to solve exponential and logarithmic equations here in chapter 4.5. So, the one-to-one property says that a to the x is equal to a to the y, which means that x can just equal y. So if we can get them to the same base, that usually will help us solve the equation. Because remember, in an exponential function, the exponent is in the variable is in the exponent this time. So we have to be able to solve for that exponent. Okay. So let's just dive in. Example 1. It says solve the equation 10 to the 4x plus 1 equals 3 to the negative x using log base x. So if I take log base x of both sides, then because log is a natural base of 10, these cancel out and my 4x plus 1 comes out in front. So that is there. And then I have a negative x comes out in front of log base 10 of 3. And then I'm going to add x to both sides. So we'll have 5x plus 1 equals log base 10 of 3. And then I'm going to subtract 1. And I'll have 5x equals log of 3 subtracting 1. That's a thing. And then I have to divide by 5. So when I divide by 5, x equals, I'm actually just going to put the negative 1 out front so you don't confuse that with the log of 3. So that would be your answer. And you could simplify that in Desmos. Here and just type it in any old thing. So negative 1 plus log of 3 parentheses divided by 5. So that comes out to be approximately a negative 0.105. Okay, the next one says solve for x. Okay, so now we have the natural number e. So we have to isolate the exponent if we want to be able to take the log or natural log of it. So that means we're going to divide by 5 on both sides. So we'll have e to the x equals 12. And then to undo this exponent, because we need x to come down here, we're going to take the natural log of both sides. And so those cancel and we get x equals the natural log of 12. And we can approximate that as well in Desmos by taking ln of 12. And that comes out to be approximately 2.48. Okay. Let's look at example 3. Some applications now. So it says, suppose a band pays interest at a rate, a bank, it's a typo, a bank pays interest at a rate of 5% compounded continuously on an initial deposit of 1,000. How long does it take for an investment of 1,000 to grow to a total of 1,400, assuming that no withdrawals or additional deposits are made? Okay, so let's go back and remind ourselves of the compounding continuous formula. Here it is, A equals P times E to the RT. And so let's fill in what we know. We know what we want to end up with. So we know that A is going to be 1,400. And we're starting with 1,000. And our interest rate is 0.05, but we don't know how long, because it says how long do we have to, so T is the question mark, how long? Okay, so just similar to example 2, I have to isolate this E exponent piece. So I'm going to divide by 1,000. And I'm going to wait to do my final computation in Desmos till I get everything to one side and isolate T. So to get my T down out of the exponent, I'm going to take the natural log of both sides to undo this E. So I'm going to take the natural log of this ratio. And then 0.05T times the natural log of E. And remember that cancels. And then to solve for T, we're going to divide both sides by 0.05. So we have a natural log of 1,400 divided by 1,000 divided by 0.05. So we can type this whole thing one calculation into Desmos. That's it. The most efficient way to get the most accurate answer. And so that comes out to be approximately 6.7 years. So approximately almost 7 years that you need to leave it sit there. Not 7 years, 6.7. So about the 8th month, between 6 years and about 9 months. Okay, example 4 says, suppose a colony of bacteria doubles in its initial population of 10,000 in 10 hours. Assume the function that models this growth is given by this function here, where T is given in hours, so that's important to know, and P0 is the initial population. When will the population of the bacteria reach 50,000? Okay, so what do we know? So we want to know T. We know something about the doubling. The doubling tells us something. So we know that it will be 20,000 when we start with 10,000, right? In 10 hours. Because we have to find this growth factor K here to be able to use that when we're going to figure out for 50,000. So if we divide both sides by 10,000, this becomes 2 because it's a doubling. E to the K 10. And then I'm going to take the natural log of both sides. So I'm going to put the 10 out in front. So 10K times the natural log of E. And remember that goes away. And so we're going to divide by 10. So K is a natural log of 2 divided by 10. And I'm going to leave that raw in my, so my real function here is P of T equals P0E. And then this natural log 2 divided by 10 times T. Because that's that's what our K equals. Excuse me. So now we want to know, when does 10,000 grow to 50,000? So, which is 5 times, right? So we're starting with 1,000, and then we have E to this natural log of 2 over 10 times t. So because we know it's 5,000, so dividing by 1,000, we get 5 equals e to the natural log of 2 over 10 t. And taking the natural log of both sides again, we get the natural log of 5 and then equals the natural log of 2 over 10 t times the natural log of e. Pencils. And then to solve for t, we're going to divide by a natural log of 2 over 10, which is really multiplying by the reciprocal. So t equals 10 over natural log of 2 times natural log of 5 equals t. So let's go to Desmos to find out what this is, how long this will take. So 10 times the natural log of 5 divided by the natural log of 2. So it's going to take not quite 24 hours, about 23.2 hours. Because it doubles every 10 hours. It's pretty cool how we can use our properties of logarithms to find and solve these examples. Okay, now that was using logarithms to solve exponential equations. Now we're going to use exponentials to solve logarithms. So when solving equations involving logarithms, combine all the log terms into one single logarithmic expression, put each side into exponential form with base 10 or base e. So we could use or base e if we wanted, and then solve for x. So let's look at this basic one. It says solve the equation log x plus log of x minus 3 equals 1 for x. So because this is a addition, we can turn it into a product. So it's really 1 log of x times x minus 3 equals 1. And that is log of x squared minus 3x equals 1. And this is really base 10. So we can really write this as 10 to the 1, right? So 10 to the 1, 10 to the 1 equals x squared minus 3x. So if we move the 10 over, we'll have it set equal to 0. So x squared minus 3x minus 10. And then the cool thing is this is a trinomial that we can factor. So we could factor that into x minus 5x plus 2 and set them equal to 0. And so x equals 5 and x equals a negative 2. Now, the only thing we have to be aware is, are either of those going to cause an issue for a logarithm? So that is the question. So let's go and look at Desmos for just a minute. I am going to turn that off. This is from another. Okay, so let's put in natural, oh no, it was log of x plus log of log of x plus 1. No, it was x minus 3. Okay. So log of x plus log of x minus 3. And where does it equal 1? Oh, I'm going to just do y equals 1. And where does it intersect, right, is what we want to find. So if you go up here and touch the gear and have it make a table, what that does is that allows us to be able to let's set this equal to y up here. Then, okay, then I'm going to go, sorry, I'm going to go back up here and again have it make a table for this equation. Mhm. I did not want to do that for some reason. Let's zoom in. I'm going to change my graph here. From 0 to 5 on the y. And then it's it's better that way. So this is 1, 2, 3, 4, 5. So we want to know where y equals 1. We want them to intersect. Oh, I'm sorry. This is actually 0.2, 0.4, 0.6, 0.81. So we're going to see where they intersect. So when x equals 5, that one is okay. But x cannot equal -2. Because remember, when we zoom out, there's an asymptote, and the asymptote's at 3. And that's because when we put 3 in for a -2 in for our answer, we're going to take the log of a negative number, which we cannot do. So let me go back to my paper. I want you to see it visually. So 5 is okay, because if I put 5 in for x, I can take the log of a 5, and I can put 5 in for x here, and I can take the log of 5 minus 3, which is still log of a positive number. But if I put -2 in, I can't take the log of a -2, and I can't take the log of a -5. So that one has to be excluded. So make sure you're noting what ones have to be excluded. Okay, let's look at example 6. Okay, so solve the equation natural log of x plus or equals 1 plus the natural log of x minus 2. Okay, so we want to combine the natural logs. So I am going to subtract this natural log. So we'll have natural log minus natural log of x minus 2 equals 1. And that subtraction is going to go into a fraction of a over b. So it's really 1 natural log of x over x minus 2 equals 1. Right? And so I can take the e of both sides. So if I take the e of both sides, this is going to be e to the 1 equals just x over x minus 2, because that natural log goes away. Now, we're trying to solve for x minus 2. So I'm going to multiply times x minus 2 on this side. So we'll have e times x minus 2 equals x. And so I have E times X minus 2 times E equals X. And then I'm going to get my X's together. So I'm going to subtract E to the X or E times X on this side. So it'll be a negative 2E equals X minus EX. And then I'm going to factor the X out. So it's 1 minus E. We'll let the calculator calculate with the E here in a minute. So we have a negative 2E equals X times 1 minus E. So I'm going to divide by 1 minus E. So it's a negative 2E over 1 minus E equals X. That one was tricky. So we have a negative 2E divided by 1 minus E. So that is X is approximately 3.16. Let me go back there. That one was very tricky. Look at our last example for lesson 4.5. It says the cumulative box office revenue from the movie Finding Nemo can be modeled by this logarithmic equation, where X is the number of weeks since the movie opened, typo, and R of X is given in millions of dollars. How many weeks after the opening of the movie was the cumulative revenue equal to $300 million? Wow. So we want to set our equation equal to 300. So I'm going to subtract 114.3 from both sides. Hmm. 300 minus 114.3 is 185.7. And then we're going to divide by the 78.05. So that is 2.379 equals natural log of X plus 1. I'm going to show you my paper here. Here we are. So we're going to take the E of both sides. So E to the 2.379 equals E natural log of X plus 1. So those go away. And so we have e to the 2.379 equals x plus 1. And then if we subtract 1, we'll get e to the 2.379 minus 1 equals x. And let's just go back and find that. E to the 2.379. And if you do a bunch of decimals, it's even better. And then make sure you arrow down and then subtract 1 so that the subtracting 1 is not in the exponent. So it looks like, and this is given in weeks, so about 9.79 or about 10 weeks. And then Finding Nemo had a revenue of about $300 million. Crazy. And that is the end of 4.5. Catch me back for lesson 4.6. We're going to do some modeling with exponentials and logarithms.